That would be quantum mechanics, because that classical mechanics and classical electricity and magnetism doesn't work at the small scale. So before we even talk about go into it, everybody remember why we have quantum mechanics? Actually, you were different quantum mechanics, so 50% of you were. Why we have quantum mechanics? Anybody? We have quantum mechanics because the problem is to observe something, you're also going to affect it, and that's basically the crux. It's the measurement problem. When you have no problem when it's big object like this. You observe it, you'd say it's at this location and moving at this velocity, and you can, after your observation, you can be sure that that's what it has. But the act of observation or measurement actually changes what you just measured. Okay, so that's the problem. So when we're talking about it being an electron, how do you know if an electron is there? Well, you have to shine light on it. You have to do something, and that photon will have momentum, and it'll kick it, move it around, right? And that kind of makes, to make long story short, it makes it, you can't talk about the location of a electron or the small particle anymore. You have to talk about the probability of where it is, not exactly where it is. Okay. And so we developed a whole kind of machinery to describe this problem. And the first thing we need to introduce is the idea of a state. Okay, so the state of a particle, state of a system, state a particle or a system is going to be represented by what's called a ket. Okay, it's you can think of it as a vector if you want, but it's a broader term. So a ket is given by this symbol, and this object, this mathematical object, you can do things like you can multiply it. By a constant, right? Say you have a constant C. So if I take a C, multiplied by U, it's just that I take a number multiplied by U. This is still same state U. So we don't say that it's changed. The state has changed. It's just been scaled by C. Changed it. You change its length, but you've kept the state the same. There's another thing called the superposition principle. where if you have two states, U and V, they actually change the state, right? You add it. So when you take a state U and a state V, you created new state W. So W is a new state. So the best analogy is just like our three vectors, right? The vector V, the direction won't change if you scale it by a constant, so it's still in the same direction. You add it to another vector that's pointing in some other direction, you'll get a new vector that's pointing in a third direction, right? In the most general case. So that here the direction is kind of like the state of the system. Okay, so that's measure the state. Now, what about the state? What's next after the state? Well, we have something called observables. And an observable is something you want to measure, basically. So, is an observable is like a position. It's a physical quantities. Quantities to measure. Right. Position. Energy. So in this particle in a certain state will possess all this information, possess information about its the position and the energy and stuff. And it's going to be represented by what's called an operator. So an observable is represented by an operator. We call it A. We put a hat on it. This doesn't mean unit vector. It just means to differentiate. When you see a hat, it's an operator. Okay. So what happens when you want to measure, say, the state U with the observable A hat? You operate on it. You take A hat and you put it next to your hat U. This operator is going to do what the name suggests. It's going to operate on it, change it, and then turn it into something, a different state, and then something else. So, for example, you might have an observer for position. And the operator would be the x-axis. And that will operate on the state operator on the state operator on U. Now, we can also, we won't get into this, but if some of you have known about, have done wave function. Okay. The position is given by x hat, and it's going to operate on u. If it up in the what's called the position representation, it'll operate just by multiplying x, the variable x. Momentum would be given by p hat, and in the if they're operating on a wave function, it'll be given by a derivative. Last example, energy. The energy operator is the Hamiltonian H. Position space, it's I H bar E by E. That's the wave function. Okay, we have your state, have your operators. You want to measure an observable, you take your operator corresponding to that observable, and you operate on your state. And it gives you a new state. Now, as we said, that's the problem. You can never, you know, it'd be nice if it didn't give you a new state. It just give you the information and kept it the state the same. But in general, it will change the state, except for a case where very special states where when you operate, they stay the same. Now, those are the states we love, because then your system is not perturbed. So if we can find a state where the operator operates, gives us the information, and the state is not perturbed, that'll be the best. Okay, and that it turns out there are those states. Okay, and that's where most of probably all of quantum mechanics is going to talk about those states. Okay, and those states are called. Anyone remember?
An eigenstate.
What is that?
An eigenstate.
Right, eigenstate. Okay, so we rely on eigenstates. Which are defined as A hat, say, we're operating on phi I, eigenstates, comma, phi I. I meaning is an index, so there's could be more than one eigenstate. So when A operates on phi I, it spits out what's called an eigenvalue, which is just a number, and it keeps the state the same. Remember we said multiplying by a number doesn't change the state. So this is called an eigenvalue. Right? And this is great because now when I do this, I keep my state the same, and I just read the eigenvalue. It tells me how much energy it has, how much momentum it has, so forth. Okay. Next thing we like to do is what's called an amplitude. Okay. So the amplitude is you operate, give you a state or an eigenstate, doesn't matter. But you want to compare it to your original state. Okay. right? And that tells you how much has changed. If you get 1, that means nothing changed. If you get 0, that means it really changed. So it disappeared. So the amplitude is sort of like the dot or inner bound. Okay. So given 2 states, U and V, the amplitude gives inner overlap. How much they overlap? How parallel are they? And we write it as VU. This is the definition. It's this V, while this is called a ket, when you write V the other way, pointing the other way, this is called a bra. So together, they make up bracket. I don't know. This is called Dirac notation. I don't know if Dirac invented the name. In linear algebra, nomenclature, the term is called the dual. Where ket is a vector, the bra is the dual vector. It's the vector space, it's the dual. So again, the analogy with 3D vectors is perfect. If you have 2 vectors, they're not the same, but they're one is almost parallel, or there's component that's parallel. So the overlap, the amplitude measures the component that's parallel. Okay, so the dot product. If it was perpendicular, there is no parallel component, so it'd be 0, no overlap. So that's a good analogy with that. And so it can be shown, and we won't get into any more details mathematically. Are you taking part in the fall? I'm not sure yet. That's a yes. I just heard yes. Are you? Okay, good. See? Yeah. What can I do to make you sure? Other courses? Are you taking EMAG? Is that what? Yeah. I think you're not. It's not required for you, right? Required for the last year's class.
Not sure if it's required. We want to get at the next year's senior year.
We required it last semester, so for the kids coming in. So then you'll be ready for. You only have 8 left. Okay. Now, forgot to mention, for a true physical system, like a real physical system, the eigenvalues lambda I must be real. Because at the end of the day, we need to, we measure this amplitude. It's going to give us a lambda, but for example, if these were both eigenstates, it will give us a lambda that has to correspond to a real number, not an imaginary complex number. This is just the requirement that we want. And okay. So for example, so if I have A and I operate on phi I, I'll get lambda I, phi I. And then I calculate the amplitude of how much it overlaps with, say, another eigenstate. Also, another word is eigenket. That's synonymous to. So a ket and eigenstate are the same. So here's my lambda I. Then I want to know this new state, whatever I measured, how much overlap did I get? And the lambda I being just a number comes out. And we have J. So it turns out that this is going to be orthogonal. It means that it's going to be 0, 0, J is not equal. So for true physical system, lambda I must be real. And I won't get into Hermitian, being Hermitian. Leave that for 431. So it has to be real. Yeah, this is have to be orthogonal. So this is called being orthogonal. A stricter thing is called, to say, normal. That means phi I phi j is actually equal to delta I, the Kronecker delta. It's 0 when I not equal to j, so I not equal to j, and 1 from I not equal to j. So it's a stricter thing than orthogonal. It's orthonormal. It's also normalized, equal to 1 when they're the same. Okay. And I think we have 5 minutes left. I think I'll stop here. We did state, observables, and operators. And the third thing will be now the actual measurement. Okay, so we need to get the number out. Okay. This is what happens. Now, how do I get the number out? And it's very close. We're almost there because we just defined what the amplitude is. We take the number out for a general system. Okay, especially when things are in more than one eigenstate, it can be in superposition of eigenstates. So what is the measurement? Okay. So this is a good preview to get you all excited. Okay, that's it. I'll send you the email about the exam, and then office hours today at 4. Are you Doing okay with the homework?
Right now I am.
Okay. Good. You? No. Okay.
I haven't followed.
Yeah.
Ask some questions.
Okay. Um,
How do you?
uh, have you watched all the videos and stuff, or
Yeah, and I don't know.
how do I have shit? Okay. So number one, actually not as bad as you might think. You want to write in the last frame. Let's say you pick one photon. This one. It has an energy and a moment, right? That energy. So this is energy of E gamma, and this is E gamma prime. Actually, let's say 1 and 2. 1, 2. You can write P1U in the full momentum of this. It'll be E1, and then E1 close by E1 prime. Right? Yeah. Yeah. Good. Okay. And then down here, P2U is P2, P2 close by, close side, minus 9. So if you, and now what is this guy? This guy is going to be the 0. Now, do the same for the center mass spring. The same. Draw this and do exactly like that. Different variables. Like maybe P1 prime, P2 prime. Okay. And in the center mass frame, because energy and momentum is conserved, you already know the energy. They have to be half the mass. Yeah. Okay. And then now you just take one of these and Lorentz boost. Do a Lorentz transformation. And set it equal to what is it? When you can Lorentz boost this, you go to there. Excuse me? Or you can Lorentz boost, that's why it's easier to Lorentz boost this. So if I'm in this frame, how do I get to that frame? Well, this one's going by. That means that usually the Lorentz transformation you have is gamma minus gamma beta. That's boosted to a straight line. But here, you know, you see this guy go that way, you have to boost to negative cross. So it only, that's the only thing. But then you can operate that on this. You have, yeah.
I almost forgot where I was, and I was about 5 minutes, like, yeah,
I'm just like, now,
Yeah, well, yeah.
on the first
Shit.
one, fine, holy crap.
And just turn in whatever you have as well. I work on whatever you have. Finish whatever you have. That's what it means.